Right. Okay, so today I want to start talking about kind of like some security fundamentals. And if you have more time, we can also talk about cryptography a little bit. A few kind of like quick announcements. Sign up sheet. I saw only a few of them already did it. It's due on Monday night. The reason is we want to kind of like find the schedules and announce the schedule so people can start preparing their slides. So find a team member if you can. If you don't worry. Just submit your own request, and then we will team you up with someone else or multiple people depending on your interests. Okay. And select the papers that you think you're the most interested in. And select as many as you are interested, because then that increases the flexibility for us to schedule. Okay. Does anybody have a problem with finding the links in the sign up sheet? Have you seen it? Do you know where it is? Do you know which paper list, where the paper list is? All right. So do it over the weekend or so, okay? By Monday night, I'm gonna start scheduling, and then uh, this is important part of your class and your grade, so make sure to do it, okay? Last time we also talked about security principles. So we kind of say that okay, from principles, we go to the policies, and from policies, we go to the implementation. So now we want to actually talk a little bit more about like real world systems. Another quick logistics, as I said, on MS Online students, pretty much everything is the same except the quizzes will be online, 24 hours you have time to start. Paper representation will be recorded. And not, of course, in person. And then participation grade would be pretty much the same on campus where you get the bonus points. Other than that, there's no, of course, opportunity for participations, but you can always like reach out to me, and then we can schedule one-on-ones if you have questions. All right. So these were like kind of like for your information, these were the security principles. And then we said that essentially the problem with the IoT is that these computers are controlling many critical tasks, right? So let's actually do a quick overview of what is IoT, what are the kind of different parts of an IoT, and then what are the security issues, and then we move on. So kind of like if you think about IoT, I always like to have like a slide like this to show you where we started. So this is kind of like the first kind of general purpose computer back in the 50s called ENIAC. And the amount of computation that this does is actually significantly less than this, smartwatch that we have in most of your wrists. Okay. So the performance was significantly less. The power consumption was insanely large. And the area was this big, like probably bigger than this room versus what we have now on the wrist. So we have come a very, very long way. And of course, the story of how we did it is multiple separate courses. But we really, from that, we are going to this these days, right? So if it's surrounded by computing devices and sensors and actuators, and it's just growing, as I said, right? So it's going to the industries and smart homes and classrooms. UCLA is going to be the last one to integrate anything smart in their rooms, so don't worry about that. But other universities probably going to have something cool soon. So the trend is essentially kind of this, right? From very large and stationary systems, now we are moving towards small and mobile systems. Okay, so that's number one trend. And as you can see, like these pictures here, we have laptops, we have cell phones, we have this kind of like wearable and small computers and devices. So basically, the trend number one that I want to point out is computers have got smaller, cheaper, and faster. As a result of this, that what we care about in the security domain is basically there are more computers controlling more things, and there are new applications generated as a result of this, right? So, for example, now you can unlock your door from your cell phone, which you couldn't do like 20 years ago. And then another kind of like, big trend is kind of like a big, change in paradigm shift was connectivity, right? So not only these devices kind of work in isolation, but now you can actually connect to these devices 100 miles away from the device, right? And this wireless connectivity has also changed the game and transformed our lives significantly in a better world, right? So now we can, communicate with various different things, but unfortunately, because it also opens the door for various different exploits and attacks. Because if I can access to something, means the attacker potentially can access the same thing. Versus if there's no connection to this device at all, then it was very hard for the adversary to also attack this device. So it kind of makes sense, right? So this was kind of trend one: more devices, connections together. The second trend is basically, as I said, is the connectivity of these devices together. We have local networks, cellular network, the internet, various different kind of ad hoc connections, and so on and so forth. And then if you think about this, this is the birthplace of what we call, cyber physical systems and IoTs. And based off these two trends, that there are more and more computers, smaller computers, there are more connectivity of these computers. We are now experiencing what we call Industry 4.0. So this is actually a picture here. It's showing like four revolutions in industry. The first one starts with kind of the steam power, and we managed to kind of build a steam engine back in the in 18th century. And then we started to actually kind of do mass production using the electrical and mechanical the revolutions and technologies. This was the 90s. And then Industry 3.0 was when we actually found and figured out how to use robots and automation in some sense. And that was kind of like, like around 60-ish years ago. And that was in Industry 3.0. And now what we are experiencing right now is Industry 4.0, and that is the kind of the cyber physical system domain that we now using this internet connected things for various different things, and it's significantly improved our industries because of that. And then there are always, discussions about what is Industry 5.0, machine learning probably part of it, and so on and so forth. But the kind of the short things is that this is a big deal, right? And as a result of this kind of like, massive amount of computation, various different types of computation, and the connectivity between them, what happens in like past few decades was that we need to have tiers. We cannot have like same computation and same kind of networking for all the possible applications that we have, right? Some applications need some form of local computing, some applications require more of a what we call a cloud computing, and some applications need something in between, right? And then another thing that happens is that because of this connectivity and the technology that we use for connectivity, this is also has a huge impact. So if I want to connect from here to my office, probably I can use some form of a short range communication, low delays. But if I want to connect to some form of server, maybe in the East Coast or in Europe or somewhere else, that requires a lot of delays between them, right? So as a result, we need to kind of decide where the computation should happen. Should it happen here? Should it happen in my office? Should it happen in the East Coast or in Europe, and so on and so forth? And of course, this kind of computation and where it happens depends on the application. If the application needs to be going to happen in real time, I don't have time to kind of send things out. I need to do it as much as possible in my own device. So this kind of, depending on the applications, this tiers kind of was born. And then of course the big one was birth of the cloud and cloud computing, where essentially the idea was I don't use all of my computational power with me. All I need to do is like a fast communication to this servers that's stored somewhere in the world that I don't know and I don't care. And I can basically just offload my computation to that. And another nice thing about cloud computing is that, the birthplace of these kind of services, this as a service things, which is, if I have a very nice, software or a machine learning model or whatever else, I can just put it into this marketplace of, this system of servers, and users can basically just go and run things using that, right? So this is all like this Chat GPT and OpenAI is a great example of why this is a big deal, because you don't need to kind of go and buy the product for them from them. You can just, they put it on the cloud, they provide an API and service to you to use it, and then you use it as you go through. And this is usually what we call kind of X as a service, and this X could be in structure, it could be platform, it could be software, it could be machine learning. So there's various different things. So the IaaS, PaaS, MLAS, all sorts of things. Um, and going back, the cloud computing is basically kind of this availability of various different services, not necessarily computation. Sometimes it's just storage, right? So for example, if you use Google Drive, which, Google is actually cutting us from the unlimited, and now we are kind of unlimited storage, databases, networking, software, various different things, right? So there are lots of services that we can use from cloud, and the cloud could be public, such as, AWS or Azure. It could be a private cloud. So many of, businesses that, for example, Google Cloud does is not to me and you as like a general public. It's so for the particular company, for example. And it could be some form of a hybrid version, of course, right? And there are a whole bunch of benefits. I'm just grabbing this, I think, from Microsoft. There is cost associated with this, speed, productivity, security, of course, because now I don't need to kind of like apply security on my own device. I can only trust, Microsoft to just do the right thing, and I can just, upload my things there, and that's it, right? So there are a whole bunch of, benefits of the cloud, but that's not the story of this class, of course. And as I said, there are all services coming to it. And then another thing that's happening is that not everything needs to be uploaded to the cloud and computed in the cloud. There is kind of a continuum between what we call in the kind of a local computing and the cloud computing. There are things that are kind of like running on the edge, like your cell phone, and your computation on your cell phone is an example of that. It's kind of completely done locally, versus there are certain things that you kind of offload to the cloud. And then you kind of like see this trade-off between them. There is like, computational power in your local device, and there is like a big computational power in the cloud. So you cannot do all the things in your own local machine, because, for example, in order to run a big machine learning model, you need a very, very power hungry GPU, which you don't have, but Google has, right? So you can actually use theirs, right? So that's kind of like the motivation. But the big thing is the connectivity, the latency, the power. Of course, there's cost and maintenance coming with it. My point here is kind of like, giving you this perspective of different ways that we can do computation, right? So we can do computation in locally, we can do computation in the cloud. And what I want to get to is that there are various different security issues coming with them, okay? But they are the reality of our, computational paradigm these days. So you cannot do everything locally, you cannot do everything on the cloud. There will be some interaction between the cloud and the local device, and we need to understand that. We need to acknowledge that, and we need to build our system such that they are secure in both scenarios, okay? And then usually there's kind of like a middle tier as well, and that's we usually call it the fog or an edge. That is kind of like, there are, different train of thoughts for this, that not necessarily everything needs to go all the way to the cloud. Maybe we can have, for example, smaller server that kind of supports more localized devices. So for example, maybe in Westwood area, we can have like a big server machine that all the kind of like, all the people in this neighborhood can just connect to that server instead of connecting to the big server that Google has, I don't know, somewhere in the deserts or something, right? So, and then the question becomes, okay, does it make sense? What sort of benefit does it have? And then that's the story of fog and edge computing. If you're interested, definitely you can go and read about them. But it's generally like we usually talk about 3 layers, not just 2 layers, okay? Yeah, it's kind of like providing some reasoning for it. The latency, scalability, and cost and maintenance is kind of the big driving factors for this. And then one thing I want to clear out here is that you probably read and hear these terms before, and you will probably see that there's some of it are kind of interchangeable. Some people use it differently. So typically, edge and fog specifically are kind of like they interchangeably being used. And when they say edge, they mean the middle layer. And but some other people, for them, the edge is kind of like the last layer. It's the IoT level. Usually what we do is kind of we use this kind of the second bullet point in this class. So we call it device, local device, or device or IoT device. That's kind of the bottom tier level. The edge is the middle layer, and then the cloud or the server is the top layer. Okay, so it's typically that's what we do, and that's what is normally also called in most of the literature. Another term that you probably might be confused is IoT versus embedded systems versus cyber physical systems. Versus, if I want to add one more, it would be smart devices. In general, they're really the same thing. At least these days are the same thing. IoT, you might argue that when you say IoT, there is kind of like implicitly there's some notion of connectivity comes to it, versus embedded is more of an umbrella term for this kind of different type of devices. And cyber physical system, or CPS, is when there is some form of physical activity involved. So there's some form of actuation or sensing that interacts with the physical world. And then the smart is just the notion of like turning something that used to be just a dumb physical thing to something that is now controlled by some computers. That's kind of like the initial thoughts behind these four different terms. But nowadays, you will see that basically they are all kind of use the same, they carry the same meaning. So you can say IoT, you can say embedded, you can say cyber physical systems, or you can say smart. I personally mostly use the term IoT, but when I say IoT, I kind of mean all of them together. Okay. Questions? All right. So if you think about, yeah.
Extra cost and security add to the whole development process. Like it becomes with the edge device.
How much cost does it have to add security? Uh, so, I mean, generally, the cost is kind of very, very subjective and very, very application specific. Good thing about cloud is, for example, the cost is kind of shared, because if I install something on the cloud, then all the users who uses that cloud service going to benefit from this. Versus if I do something locally, then I need to go through every single device and do that. So there's this notion of aggregation comes into the play when you have some form of a cloud service. But I mean, how much we need to spend, that's really a tough question to answer. It really depends on the application, the customers, the workload they have, whether it's just software, whether it's hardware and software, operating systems. It's actually part of things we're going to figure out in this class. All right, so if you think about computer systems in general, whether it's an IoT or CPS or a PC or it's a server or it's cloud, whatever it is, if you want to kind of break it down, it's usually these five elements. There's some sensing involved. Usually that's the input to the system. Without input to the systems, kind of things are meaningless, right? So you need to kind of somehow input something to the system and receive an output. Otherwise, what's the point? So there is some form of sensing involved. And keyboard, you can even think about keyboard as some form of a sensor, right? It sense the pressure of your fingers, and you send some form of an input to the system, right? So when I say sensing, I mean any sort of input-output device, okay? Then there is some form of processing, and the reason that I put local is kind of it happens on the device that the sensor is connected to. So this processing could be as minimum as just sending this to the cloud, or it could be just the full computation can happen on the local device. Then we usually have some form of networking if this is connected to some form of, an edge cloud continuum. So this network could be various different things, could be wired or could be wireless, could be different technologies such as Wi-Fi or Bluetooth or Zigbee or anything else. Then, of course, there is some form of a backend. There could be an edge device, or it could be a cloud device, or it could be both of them. And then we usually go back to the device through the network, through the local processing. And this is where we're going to have our actuation. Okay, actuation doesn't happen in the cloud. This might be a little bit confusing. What I mean here is that it's kind of like there's just different elements. Of course, not all the computers have all the elements. For example, your small Raspberry Pi is just basically sensing, local processing, and actuation. There might need even no network to the system. But many systems these days have all the 5 elements, okay? Has some sensing, has some actuation, has processing, network, and edge and cloud, okay? And the computer itself, you can think about this as kind of basically hardware, software, and operating system. So this kind of local processing itself has these 3 different components. And then again, this operating system part is optional, which means that not every system has an operating system. Some system has what we call a real-time operating system. Some people are basically bare metal, which means there's just software and hardware. That's it. And the interesting thing is that we're going to talk about actually a lot 2 weeks from now is this interaction with the physical world. And this interaction usually happens during the sensing and during the actuation and a little bit during this network activities, right? And we cannot live without this interaction, and it's very important because we need to kind of have something to the world. Otherwise, what's the point of computation? And then there's also interaction to the digital world, which means that we have the internet, we have network. Many of these devices have multiple processes from multiple different users, so it's not just one user using this computer. There are multiple users, especially when we are talking about the cloud. You rarely have just one user in the cloud. You have many users in the cloud. So there's also interaction between these different users that might have impact your system. Okay? So now going back to the security discussion is that now that we understand these, what is the attack vector? What is the threat model? Which of these parts do you think is actually vulnerable to attacks? Suggestions? Yeah. Network, okay. Sensing.
I would actually say there could be a vulnerability in all of them.
In all of them, right? So the answer is really all of them. So all of them, actually, there are instances of attacks. There are attacks to the network, as you said correctly. There are attacks to the sensors, as you said correctly. There are attacks to the local processing, as we're going to show it a lot in this class. There are attacks to the actuation, and of course, there are attacks to the cloud. So the threat model in this system is what is the target is every single part of our computer is a target. And unfortunately, all of them has been attacked and will be attacked, and we need to defend them all. Okay, there's no single point. And if you remember last time when I say we need a complete mediation, we need to actually think about all of these things. Okay. And then what is the status quo? What are we doing now? Unfortunately, kind of like we didn't really care about security as kind of the primary factor when we were designing all these systems. When we were designing our network protocols, we didn't really care about it. When we were designing our computer hardware, we didn't really care about it. When we were designing our sensors, we didn't really care about it. And in general, we didn't care much about security most of the time. What was the kind of like the main thing that we care about? Any suggestions, do you think? What was the main thing? Yeah.
Speed and cost.
Yeah, speed and cost, right? The performance, and then secondary, some form of a cost. And then if you want to throw in, it's probably power in some cases too, right? So we care about these. And then if you think about this, when you're buying things, also, you probably think about these things, right? You don't care about like whether this is secure or not, but things are changing, right? Now you start thinking about, oh, whether this product that I'm buying is secure or not. I gave you an example of the casino being hacked, last lecture. And now the next time this company wants to buy software, they're gonna think twice about whether the system that they're gonna buy is secure or not. And the reason is that it's not like things are changing. It's because now the cost, also the security is kind of embedded in this cost, because I told you that if, for example, the system is down, there's going to cost billions of dollars. So maybe now it makes sense to I paid another 100 million to buy the software, but like, there is like 5% less chance of my system being hacked, right? So still, economy and economical decisions, financial reasons is the main driving cause. What has changed is the fact that now the cyber attacks really cost companies something. Now they're starting to, well, okay, now actually seems that they need to do something about this. That's what's really changed. It's not like, oh, we became aware of security as this very, grand thing. It's still that, companies saw that, oh, if their system is not secure, they're going to be lawsuits against them. They're going to lose data. They're going to lose services and so on and so forth, right? So that's really the reason. Questions? But I mean, the reason that we kind of recently realized this is just because of these real attacks that is happening. Okay, the impact of the attacks is kind of like was a wake-up call for us. And then what's our current strategy? Current strategy kind of whack-a-mole strategy. Okay, because many of these systems are what we call legacy systems, right? You cannot go and like change all the locks in these hotel rooms. You cannot like change all the devices in this big, I don't know, factory. So what you need to do is kind of like say and pray and hope that system is not attacked. Of course, you can do some measures, but if something happens, you will react with. Okay, so that's really what most of these companies do these days, that they don't really do anything unless something happens. If it happens, then I need to do something about it. Okay, so that's really kind of the strategy at the moment. Because again, it's really hard to kind of go and change things. But of course, in future, what we need to do, first of all, one thing to understand is the trend in future. What is this security problem going to get better or worse? And the answer is that it's going to actually get worse. The two reasons. One is there are going to be even more devices, right? Obviously, what we're seeing now is we are buying more and more electronic devices ourselves, and that's kind of expanded to every other person that we know. And the second thing, so it's kind of like some numbers, 200 billion devices 2020, $11 trillion 2025. This is just the market cap of this cyber physical system IT business. And the second thing is that they're just controlling much more critical devices. I gave you an example last time. I'm going to repeat it again, that your bank account, your lock at home, a car, I don't know, like your messages, emails, everything now is electronic, right? So the opportunity for being hacked significantly higher. So it's much more difficult to kind of like even more difficult to secure these devices. So that's the future trend. Okay. So kind of like to recap, what I was trying to kind of say, the message that I want to send is kind of like reinforcing what we said last lecture, and that is that if we are going toward this direction of systems are becoming more and more vulnerable, and then we provided some reasons for it, and we need to start thinking about what should we do in order to secure them. Okay, that's kind of the idea that I was trying to kind of give to you in the past two lectures. Okay, any questions so far? All right, so now that we know this, let's also take a step back and see what is kind of like, how do we build secure systems nowadays? Like, we are not like, I told you that we didn't care, but it's not like, this is like a completely new thing. Of course, we spent some time and thinking about this. And there are secure systems nowadays as well. So how do we build that secure system? So we're building secure systems are based on this very fundamental idea. And that's, the trust should start from somewhere, right? It's kind of like a chicken and egg problem in some sense that, there's a chicken and there's an egg. So we have the kind of like, the egg, that is the trust. So we trust something. I'm going to explain how do we trust that. And then we build everything around it. So if I trust something and I have a mechanism to trust other things based on trusting this, then I will have a big system that I now trust everything about. Okay, that's kind of the idea of how we build secure systems in our computers. So what do we trust, that you might ask? And the kind of the principle that we are looking at is there should be something that we design very carefully, and hopefully it's simple enough that we can kind of verify and check to see whether this is tampered with or not, so we can somehow verify this, hopefully based on some theoretical foundation that we know. And that would be what we call our root of trust, or our base for the trust. Okay. And then, of course, the second question would be, what are the candidates? Is it hardware? Is it software? And the answer to that is usually we trust very small component in the hardware. Okay. So we trust this part of the hardware, and that's usually part of, like, logic and memory together. The reason for it is logic is really like physical gates. So if I actually can see that I built those physical gates myself, I can visually kind of verify that, right? So, and if I know that, kind of like, if I have it written, that's kind of, oh, this is what this is supposed to be, and then I see it and verify it, I think that's enough for us to trust. And then the good thing about hardware is it's hard, which means that it cannot be changed, right? So if I have this processor that's built this way, tomorrow it's going to be the same thing. Nobody can come and change this. If they do, the system breaks most likely, right? So we are safe. For memory, it's slightly different because memory can be rewritten. So if the memory is not writable, then we can trust it fully, because I can write something to it and I can make sure that it's what I intended to write. But if it's kind of like a RAM kind of memory, then I need to be careful. Every time that I want to trust it, I have to verify it and make sure that it's not been overwritten, right? So logic and memory seems to be a good starting point for us, okay? But now the question becomes is, okay, I can build kind of like a tiny bit of hardware and I can trust this, okay? So what now? Ideally, what you want to do is that if I trust this, then like the basic question is, can I do everything in this? Because that's what I trust, right? So if I can, everything I want on this piece of hardware, then that would be great, because almost all the problems will be solved. And the answer to that is, of course, is big no, because hardware is really, really limited. And if I want to do everything in hardware, I need to design hardware, and designing hardware is very, very inefficient thing. So those of you who have some form of RTL and hardware experience probably have seen the struggle of doing basic things in hardware. Versus software, very nice. You can just write things, high-level languages, Pythons, everything, right? And then whatever functionality that you want, you write it, piece of cake on software, and that's it. So for example, I don't know, if I want to invert the bits, it's very like 2 lines of code in C, versus if I want to do this in hardware, probably lots of codes to write, right? So great, hardware we can trust, small portion. But the problem is that I cannot really expand this to do everything I want. So I need some form of software to kind of help us, okay? And then we need layers of software. We don't only need one software. We need a bunch of different, applications together. We need firmware, we need operating system, we need a whole bunch of different applications. So things get really, really crazy very quickly. And then the question becomes, can we trust software or not? And, the way I'm writing it, of course, the answer is no, right? Why? Why can we not trust software? I mean, on paper, we can design software and we can verify software and all those things. And there was lots of research in that area. But there are 2 main problems, and that's the 2 problems that we're going to actually focus a lot in this course. The first problem is bugs, that you think that you designed something, but in fact you didn't, okay? Or in the process of designing that, you actually introduce some other problems. We're going to talk about this memory vulnerabilities, things like, buffer overflows and return-oriented programming and all those things. Use after free and a whole bunch of those things. And you will see that there's like, gigantic list of bugs that we introduce that cause security problems, okay? And you might ask, okay, why are we having bugs? And then probably if you have done any sort of software engineering, internships, you know why we have bugs, right? Because it's very complex things. It's thousands of lines of code. You think that you're doing a good job, but you don't, because it's just a very error-prone process. You got a question?
Yeah, I was just gonna say the other thing is because there's, like you're saying, different layers, right?
Yeah, and then yes, and then the comment is there are also different layers that you might do a good job on your tiny function, but then when you put this function in this rest of this big system, then things break because of the interaction. So it's not like just my code, it's the interaction with some other codes that's kind of cause problems, right? And actually, one interesting thing is that nowadays vulnerabilities become very, very complex from hardware to just software. So what used to be, oh, let's figure out software to figure out what's happening is now there's like this very extra complex things between the hardware software that now cause the bugs. Okay. And then we're going to talk a little bit about this in this course as well. Yeah. So the question is, aren't these true for hardware bugs as well? True. So there are hardware bugs as well. The only reason that there are slightly less hardware bugs is we actually follow very methodological, format for hardware, because just building hardware is so hard. We kind of do test and verify very much, lots of steps. Like, we did it, we do it, we come back and check it, not because of security bugs, but because of the timing violations and, process variations and all those things. So we indirectly managed to fix lots of security bugs because just the way that we approached hardware was much more kind of algorithmic and much more checking and checking. The second thing is that like lines of code in hardware very less than software. So much easier thing to kind of verify. But there are hardware bugs, like not even security related, just functional bugs. There are billions of them in many of the systems, right? And so this number one. The second problem, which actually we're going to talk about, is that your system might be perfectly fine. There might be 0 bugs in your system, but since you are interacting with the world, with the physical world, the physical world can manipulate things and actually create errors in your system. We usually call this, faults or generally sensor attacks that, for example, your system's supposed to work at this particular temperature or voltage point. But if the attacker manipulates that, then your system starts to behave differently, and that will cause another problem. So 2 things that kind of cause these issues that we are in, this mess that we are in. One is the bugs, main issue. Second issue is that we didn't really think about an adversarial war. And as a result, the adversary can kind of like play with this, manipulate this environment, and cause these different issues. Okay. So what happens then? Of course, what happens then is, like, as I said, this mess that you're in, that, the one way or another, the adversary takes over. Once it takes over the software, part of the software, all of the software, part of the hardware, all of the hardware, and basically game over. Okay? So what do we do now, kind of like, to provide a little bit of more detail? As I said, the current method is that we start with something small and we trust that, and then we gradually increase our trust to other components in our system. We call that root of trust, or ROT. Okay, root of trust. And this root of trust is where we think that things are okay. Okay. Afterwards, what happens, that's a different story when we're going to talk about this. But at the very least, what we should do is being able to properly boot the system into a good known state that we trust. And we say, okay, at this point, I know that the system works correctly. There's nothing wrong with the system. What happens after is like a whole bunch of complex things at the software and the interaction level that I need to figure out, and we're going to talk about it. But at least this is should be the fundamental, the basis of any system that we build. Okay, that's kind of the idea. And then, as I said, what happens after is just it's a war. But as I said, what we do at this point is that it's not like we are completely defenseless. There are various things that we do and we have developed. We do multiple things. We do isolation, we do verification, we do monitoring, and of course, there is always a chance for us to do better design, to make sure that our system is less buggy. We consider various different adversarial, environments and so on and so forth. So there are things that we do, and we're going to discuss all of these in the class as well. That, it's not just say that, oh, okay, there are bugs. So yeah, our systems are not secure. We actually do things to fix this. Okay. And then last thing I want to talk about, and I used to talk about this in this class, but now we don't do it anymore. And that's the basic assumption that I gave you, that in hardware we trust. In fact, this is actually very false and wrong thing to say, that in hardware we don't trust anymore. And the reason for this is, if I think that I built something, so for example, I have an RTL design, I need to send this to some form of fab, right, to build an actual chip for me. Okay. I'm completely at the discretion of this fabrication company and the designers of that fabrication company to follow this format that I think it is. But what if they decide to add another line to this or change this to something else, right? So to change this to something else, remove a gate, add a gate, change the inputs, change the outputs. And then we're talking about billions of transistors. It's not something that you get your chips and say, oh, you change one gate in this billion transistor system, right? So it's not, even with X-ray, you cannot do it. It's not something simple to detect, okay? And which is what we call hardware Trojans. And this is a huge problem, okay? Again, we used to have a dedicated lecture about this. We don't. So generally, the idea of this hardware Trojans is that the supply chain is also now impacted. And then there are a whole bunch of political issues around this, especially the fact that we don't really build our chips anymore in the US, for example, and we ship it out to other countries, especially to kind of Eastern Asia. And given this, the relationship between countries are not really good. Now we have much more worried about do we really get the hardware we think that we are getting or not? And the solution for this now is, of course, first of all, going and physically secure the fabs. For example, it's built mostly in Taiwan, so let's actually go and put military, units in Taiwan and make sure that it's, safe. But the problem is that, this is not this is a physical problem. So maybe it's a good idea to actually bring it back to the US. And we probably heard about this CHIPS Act, billions, hundred billions of dollars of investment, which the idea of that is, let's actually build fabs in the US, because then we can go and make sure that nobody is messing around with our designs. And maybe for our cell phones, we're not that worried, but maybe if this chip is going to go into our F-31s and F-16s and the fighter jets and tanks, maybe we care about those, right? So maybe it's better to build them here in the US, but we don't have the technology right now. So these are the things that at a very high level we have to think about. But yeah, again, so this hardware and trust is also kind of a very, very interesting story that we don't have time to talk about in this course, but just keep that in mind. Okay. All right. So let's have a quick break, and then I'm going to talk about what exactly do we build this? How exactly do we build this piece of hardware? Let's continue. Okay. So as I said, the idea is that let's say that we don't have the hardware Trojan problem. That's a separate problem to solve. Well, let's say we can trust hardware, but and then say that, okay, this is the approach that we're going to follow, that we're going to build something small in hardware. We're going to trust that, and then we're going to create a mechanism to kind of bootstrap the trust from there all the way up to the software, okay? And as I said, basically what we are looking at is some form of small hardware that cannot be modified, changed, and we can kind of easily verify. That's kind of the idea. This is what we call trusted platform modules, or TPMs. in most cases. Different companies also call it a little bit differently. Secure enclave, which is kind of like actually a little bit more sophisticated than TPMs. It's basically this piece of hardware that's very carefully designed in order to be secured. Okay. So what is the threat model? The threat model is like a hardware threat model. Once we learn more about hardware, we're gonna actually we have like a big section about like trusted execution environments and so on. So we're going to revisit this, and then we're going to basically explain this in more detail. But generally, there should be something that's kind of like the hardware should be designed such that it's secure against those kind of different attacks at the hardware level. TPMs usually follow a set of standards. There's like this working group for TPM. That kind of come up with the standards of version 1, version 2, and so on. And essentially, TPM is where the trust starts. When we kind of boot the system, like we turn it on, essentially the first thing that takes over is the TPM, and that's the process of what we call secure boot happens. And then the TPM kind of pass the control to the operating system or the system software, depending on whether the system has an operating system or not. And at that point, we kind of like know that our system is secure. As I said, what happens afterwards is really out of the control of the TPM. There are extensions of TPM that we're going to talk about. It's called trusted execution environments, which the idea is that can I use TPM in dynamic fashion? But what I want to discuss now is mostly just when I start the system, when I build the system up and boot it up, I want to make sure that the system is secure. Okay. So you might wonder, okay, what exactly needs to be kind of like put into this TPM? And usually what it has is some form of data and memory, like it's some small memory to kind of store some small code, which is the boot code, and then some functionality to verify that different components or systems are actually not modified, right? So because the whole point of this trust is we put some initial things into our system. This could be software or hardware, and we need to make sure that these things that we put in our system are not modified, right? If this the same thing that we think that it is, then we are safe. So we need to some functionality to verify that this is indeed hasn't been modified. Okay. What we usually how do we actually achieve this? We usually use some form of cryptography functions in order to see that whether this particular software has been modified or not. Those are digital signatures, secure hash functions, and so on and so forth. So we use that to kind of check whether these things that we initially inserted into our system is not being modified. If we ensure that this is true, then you're going to pass the control to that software. The software takes over, and then the story begins. Okay. Of course, the question becomes, what are those cryptography functions? And that's the first thing that we're going to talk about after this lecture. I'm going to give you a little bit of background on cryptography so that you can understand a lot of these things. Okay. But yeah, this process of the TPM. The main role of TPM is the secure boot. As I said, the secure boot is basically the sequence that we start from this initial tiny bit of code that we put into the TPM. The TPM, then you can think about it as this, that this is kind of what we trust. Within this is kind of like tiny bit of memory and tiny bit of a processor. Then there's like this gigantic memory that we don't really trust, right? But all of our code are stored there, right? Like our operating system is stored somewhere here. So what we need to do is that we need this system to kind of verify that whether this has been modified or not. So what it does is that it goes through this untrusted memory and starts to compute some form of hash of this and compare it with the hash that is stored, the hash that knows that if this wasn't modified, this should be the final results of the hash. By the way, I'm going to talk about what is a hash later, but probably some of you know what is a hash. It's kind of like, think about it as a function of input and output. So it's kind of map an input to an output. So if things are not modified, this is the results that I'm expecting, okay? So what this TPM does is basically doing that. It just checks the memory, computes the final value, and see if that final value is equal to the expected value. If it does, then it means that I can trust that because it means that it hasn't been modified. And since before in the offline phase, I've managed to verify this, now I can trust it during the dynamic phase of our system, okay? And then usually this is an iterative process. So we don't really kind of like go through the entire process and then boom, verify everything. The idea is that I start with very tiny bit of code, okay? This code kind of verifies something larger, okay? And then we trust this, okay? Now we pass the control to this larger code. And then since I trust this, now I trust this. I'm kind of bootstrapping the trust. Then I use this code to kind of trust something larger. And then if this is also passed the test, now I trust this and I kind of follow along. The reason that I'm not really starting with the big one, because remember that I need to store this into my TPM. So I want to store as minimum as possible inside my TPM and having a mechanism to kind of chain this trust all the way up. Okay, that's kind of the story of the system. Eventually, I'm going to kind of verify the kernel, the OS kernel. I know that this is the signed version of my kernel. If I can verify that, that means that I can start trusting the operating system. Then I pass the control to the kernel. Then the kernel will kind of launch all the other pieces of the operating system. And that's where I'm going to pass the control and say, okay, I did my job. Then it's you and your ward operating system, right? So the operating system takes over. Then that's where you're going to start messing up and kind of ruin the whole entire system, right? So that's where we're going to interact and run all this buggy software, etc., on the poor operating system, right? And the operating system itself is actually very buggy itself. So that's kind of like story of what we call a secure boot. Okay, there are like details of like how we actually kind of change this and so on. I specifically didn't mention it because we need a little bit of cryptography before we actually come back to this and talk about this. Yeah.
How did you know the secured hash? How did it calculate it to the person? Because
so the question is, how do we know the correct answer, right? Because we are the developers. Let's say we are Linux Foundation. So we know that this is the correct kernel, okay? So we write that, we compute the hash as we kind of did it. That will be a number. We're going to save that number inside the TPM. That's how we're going to do it. And then the same thing for any other driver. So any driver that we download, for example, if you need to kind of verify the drivers, it comes with a signature. We save that signature inside the TPM. Make sense? Any other questions?
but when we download anything in the driver, so that means the driver is not present. So the signature is also not present, right? So how do we ensure that the original is correct?
When you download the driver, you download the signature from it. That's why you have to download it from like reputable places. If you download something fishy, then it's on you, right? So then the system is compromised. But the driver itself is not part of TPM. It's operating system is the one that's kind of verified this. If you actually pay attention, you see that, for example, some of these operating system doesn't allow you to download random things. It's going to block you, right? And you have to go and manually say, oh, okay, you know what? I got this, trust third party, whatever, right? That's the reason. But you can, and that's part of the problem, that you download just like malicious application into your system and that compromise things. So don't. Anyway, so that's the security part. Then, of course, after that, that would be the operating system job to kind of keep track of things. And as I said, not necessarily all the systems have the operating system. Some systems are bare metal, so it means that the software, whatever the programmer programs into the system, that will take over. So when I say operating system, I mean like the system software. There are very different strategies at the operating system level to keep things secure. Again, isolation, verification, always verification, monitoring, intrusion detection. There are a whole bunch of works that's done at the operating system level in order to keep us secure. Of course, that's not enough because, first of all, the operating system itself is very complex software. So some of the problems are actually coming from the operating system itself. Okay. And the second thing is that, there are a whole bunch of, interactions that really this operating system cannot do anything about this. Then, of course, we're going to have the network that comes also into the play. And then there's software and malicious software and all those things. So then these all kind of like, build on top of each other. And then basically at that point becomes the battle between the designers and the attackers. And as I said, what if the system doesn't have an operating system, such as like an RTOS or a bare metal? Then in that case, we usually have a mixture of some offline compile time, security mechanisms, and maybe minimal hardware support in order to fix the system. But as a rule of thumb, system that doesn't have an operating system, usually much less, capable of defending themselves against attacks because there's nothing really kind of monitoring anything, right? On the other hand, you might also argue that since these are simpler systems, they might be less prone to attacks. That's also a true argument. We're going to talk a little bit about these future when we talk about this. We revisit this a little bit, okay? If you're interested to learn more about like how this individual systems are kind of working, there are nice white papers about various different companies. Like Apple has really nice, white papers explaining how their secure boot and how their secure kind of like environment works. Intel has, various different, hardware tools for this. They explain their PPMs and so on. Google has its own. So yeah, there are a lot, all the big companies have some form of usually high level. It's not like really going into the detail, but in order to kind of like see how these things that I said is kind of, applicable to real world products, you will see that it's kind of like, similarity there. Okay. So just read it as an optional reading. And then of course there are more things that we need to worry about. So this one is just booting a regular system, but we have things like virtual machines and hypervisors. So not necessarily you kind of like boot just one operating system. Sometimes you need to like build multiple operating systems. So then there's the story of how the hypervisor helps and so on and so forth. So we're going to get back to these, as I said, in the very last part of the class. Okay? Any questions? And as I said, the hardware itself cannot be really trusted. As I said, this is the part that we're gonna talk a little bit about when we're talking about side channels and stuff like that. But the hardware Trojan parts, I'm not going to talk about anymore. So yeah, so the summary is that we trust something basic. We build up the trust on top of that. We have fairly good, mechanisms to do this. So I would say the secure boot process is actually one of the most secure things that we do nowadays on our computer systems. The problem, though, is really that's the beginning of our computations. Most of the problems happens really after. Okay. And then for the rest of this class, we're going to talk about this after, like once the system is boot, what happens next. Before that, let's talk about crypto a little bit because you need some basics of cryptography to understand kind of the later half of this course. Okay. How many of you have any knowledge about cryptography, like, RSA, AES, shows of hands? A little bit. Okay. So what I'm going to go over in this lecture and the next lecture is we're going to go over concepts, okay? Intuitions, high-level concepts. It's really not going to go over a formal, cryptography course. There are very good courses for this. There's actually a proper cryptography course as a grad level course in the CS department. There's also an undergrad computer security course that kind of goes over the cryptography a little bit more. Here, I'm kind of give you a nutshell of kind of the idea, okay? So it's really not, I'm not going to provide any proof. I'm not going to show you any theory. I'm just going to give you the high-level concepts, okay? So there's a disclaimer. So the first question is like, why do we need cryptography, right? And there are simple answers for this. Of course, the main thing that comes into the mind is because of the communication. We need to encrypt everything that we send and receive. But there are also other things to it. If you want to authenticate someone or some quote, like the one that I just described, like if I want to see whether this software has been modified or not, we use cryptography. In order to trust a particular user, to authenticate that this user is the same user that they say they are, we use cryptography. So there are actually other things that we use cryptography for beyond just encrypting and decrypting messages that we probably heard about. So in more generic term, we use cryptography for confidentiality or privacy, essentially to know that only the communicating parties know the message. We use it for integrity, which means that we are guaranteeing that the data or the message has not been modified. And we use it for authentication and trust, which means that we are proving or showing that something is true or genuine or valid, right? This could be identity, this could be computation, this could be combination of various different things, okay? So the foundation of cryptography is this, basically. Very similar to the secure boot things. We are basing our foundation into things that we believe is true. We kind of facts, okay? The nice thing about cryptography is that these facts are usually mathematical facts, okay? So we based our assumptions on some theory that we know that is true. Although this is kind of like an asterisk here that, you know, some of these things, once the math evolve, might change, or some of them are technology dependent. So as the technology evolve, they might change as well. So cryptography, like anything else in security, is not completely immune to this kind of cat and mouse problem of attackers and defenders, but it's a little bit better than the rest because everything is very nicely theoretical and kind of chained together. Okay, so we usually start with some basic mathematical assumption, and then we're going to prove our way to the top theoretically that, you know, if this is true, we can show that this also true, which is much better than many other things that you have at the system level. But as I said, there are 4 different challenges. One is assumptions might be proven incorrect. Assumptions may not always be correct. So there are, like, for example, technology changes. Then always introduction of, you know, implementation can introduce issues similar to any other software. And then the 4th one is the problem of what we call side channels. And we're going to talk about what these side channels are later in the class. So these 4 problems are kind of like the killers for cryptography. Other than that, it's actually a very nice and neat system. So to give you kind of like a very high level overview of what we call a crypto system is kind of consists of 4 different, you know, components. There is a secret, and there's always a secret involved. And we usually call this a key. And this secret is usually shared among multiple people, or in some cases, it's like pair of keys that's shared or not shared between people. The security of a crypto system is, you know, hanging on this key, this secret. If the secret is no longer a secret, then there is no guarantee that your system works. Other than that, everything else about the system is completely known, okay? So cryptography is usually an algorithm. This algorithm could be an encryption, it could be decryption, various form of encryption, various form of decryption. It could be message authentication code, it could be hash functions, it could be anything. And then, of course, like any other systems, there's an input and output. Typically, if you're talking about encryption, the input is called the message, and the output is called ciphertext. So we usually call it a plain text and ciphertext. Ciphertext is the encryption of the message. The plain text is just the plain text. But as I said, not necessarily encryption. Decryption is the only function. There could be hashes and signatures and so on as well that we're going to talk about as well. Okay. And then if you remember, I said security by obscurity is a bad idea. As a result, everything about the systems except the secret is known to everyone. So there is nothing secret about the algorithm. So all the algorithms that we use, every single line of it is public and known by everybody. Okay. And then as you will see is that most of our crypto systems, we are going to claim that even if I know the input and output, I still cannot find the key. And that's very, very strong assumption. And we're going to show how it's actually working that way. So it's not like, oh, I don't know the message, or I don't know what is the kind of encrypted version of this message. Even if I know all of that, and if I know a lot of pairs of these, as long as they're finite, there are guarantees that shows that, the key cannot be known. Okay, so this is a very powerful thing. So the story of encryption is actually kind of started with, similar to many other things with World War II. Like the very early kind of version of a real crypto system is the Enigma machines. How many of you have watched this movie called Imitation Games? Yeah, some of you. So there is actually the movies. I definitely recommend to watch. It's a very fun movie to watch. It's also relevant to this. The story of this guy called Alan Turing, which is like one of the very, very prominent researchers in computer science. So many people call him the father of computer science. And the story of Enigma machine is that Enigma machine was this kind of typewriter, as I'm showing it here. That's used by the Nazis, the Germans, to encrypt their messages, okay? So, and then the way it was working was there was this kind of like, if you actually look into this, like this part, there was this wiring that's kind of like wired one word to another, okay? And they were changing this every day. And the way it was working was like this change, they kind of like, they know the pattern of this changing. So I know, for example, today, this one is mapped to the other one. Tomorrow, A is mapped to S, and the other day is A to map to E, and so on and so forth. And then as long as the sender and receiver on the same page, they know the exact same mapping, they can send messages together and nobody else will understand what they're saying because nobody knows what that kind of wiring is. And as long as this kind of figuring out this process of what is this wiring takes so much time, nobody can kind of like reverse engineer and figure what that is, okay? And if you, for example, those of you who watched the movie, you probably saw that, the Allies was trying to break it. And at that time, there were no computers. So what they were trying to do was kind of like literally going through the brute force approach of trying to see if they can find a meaningful mapping between the words that they're seeing. And kind of you have to go through every single iteration of the words, right? So for example, for A, 26 possibilities if you're talking about only characters, for B, 25. So it's kind of 26 factorial kind of different permutations exist for such a system. Of course, it takes days for this. And then since every day they were changing it, they were fairly secure in that sense. Eventually, this Alan Turing guys and his colleagues managed to kind of build some form of a machine that can very quickly kind of like check these different combinations, and they managed to break it. There are reports that essentially the last 2 years of the war or something like that, the Enigma machine was essentially broken. So the Allies was kind of access to all the communications done by the Nazis. And there are also reports that this kind of helps significantly to shorten the war because there were lots of, operations that the Allies were prepared for, and they managed to kind of like, be prepared for that. There's actually a nice website called enigmadevice.com that this kind of like a puzzle. Every day they have a mapping that you have to figure it out. I don't know, those guys, have you seen Wordle? This puzzle game, pretty similar to that one. So you can actually kind of like guess the words. It's usually like a nice sentence or statement. So I definitely recommend to playing with it a little bit. But yeah, this is kind of like one of the early examples of a crypto system. But of course, Enigma wasn't a proper crypto system because it wasn't secure. The reason that it wasn't secure is that they managed to break it. The reason that they managed to break it was they kind of used this pseudo-random substitution of words. They didn't do a real proper, fully random substitution that I'm going to talk about. So if you think about the cryptography methods, there are actually two main methods for cryptography. There's what we call symmetric, and there's another one called asymmetric or public key cryptography. So you probably have heard about symmetric key cryptography and public key cryptography. The differences between them is the symmetric key is that there is one key that is shared among all the users, okay? So there's this thing called secret key that everybody who wants to send and receive things, they have to use that. So as a result, for encryption and decryption, the same key is going to be used, okay? How do we actually share the key? That's a separate story. At some point, we're going to talk about this, but assume that somehow everybody knows the key. Asymmetric is kind of like trying to solve this problem of how do we share the keys. And in asymmetric, instead of having one key, we have two. We have what we call a public key and we have what we call a private key. The public key, as the name suggests, is public. Everybody knows about this. The private keys should be kept secret by the user, okay? And as I'm going to describe, for encryption, we usually use the public key. For decryption, we're going to use the private key in order to kind of, use the system. I'm going to talk about symmetric first, and then I'm going to then talk about asymmetric. The main one in symmetric that probably you have heard about is AES. And then in the asymmetric, the famous one is called RSA, all right? So before jumping into that, there's also one thing that I want to talk about, and that's what we call cryptography primitives. Encryption, decryption, secure hashes, message authentication code, digital signatures. These are what we call cryptography primitives, okay? I'm going to talk actually about all four of these main primitives. And these are the main basic blocks of building protocols. On top of these primitives, there are protocols. So for example, you probably have heard about TLS, right? Or SSH, or I don't know, zero knowledge proof, or a multi-party computation. These are protocols that build on top of these primitives, okay? So TLS is not a cryptography procedure per se. What it is just combination of these primitives kind of, combined together in order to achieve what we call a TLS, or what we call a network, security, and so on and so forth, okay? What we're going to talk about is these primitives, okay? These main four ones that usually you will see in every single protocols. The protocols, we don't have time to talk about them. A little bit of blockchains you're going to see in one of your projects. The rest, if you're interested, you definitely can go and read about them. Like how do we actually do internet security and all those things. Once you know about these primitives, then you will understand those protocols if you follow them along, okay? So the first thing I want you to focus is encryption, decryption, okay? So mathematically, encryption, decryption is this problem of this, that encryption is this function E that takes two things, the message and the key, and then it creates this output we call ciphertext, okay? We call this ciphertext, we call this input message or the plain text, okay? And then the problem of decryption is the opposite of encryption. We use decryption with D. And as I said, we're going to focus on symmetric key encryption and decryption. As a result, you can see that this key and this key are the same. If this was an asymmetric one, this was a public key, and this would have been a secret key. I'm going to talk about that later. So in decryption, you get the ciphertext as the input, and you get the message as the output. Okay, let me just change the presentation really quickly, and then I will be. Great. So, love your full on into cryptography. Talk about these. All right. So Let's focus on symmetric key encryption decryption. The main property that, like, the very intuitive property of any crypto system that we use for encryption is the correctness property, which means that the decryption of encryption of a message should be the message. That this should be what we call a lossless system. That the message that I'm encrypting, if I decrypt it, of course I should get the same message. If I get something else, then there is no point of doing this this encryption mechanism. Okay, there are other optional properties. Some of these encryption, crypto system has it. Some of them don't. For example, there is this thing called homomorphism. Okay, so what is a homomorphism? The homomorphism is that if I have a function f, let's say this is a polynomial function. Okay, if I apply function f to m1 and m2, let's say, for example, this is an addition. The function that I'm interested in is addition. Homomorphism says that this crypto system is homomorphic over the operation f if f of m1 and m2 is equal to the decryption of f of encrypted m1 and encrypted m2. Okay, so let me give you an example. Let's say f is basically an app. Okay, so let's say I have message 1 and I have message 2. Okay, let's say I encrypt message 1 and I get C1. Let's say I encrypt message 2 and I get C2. What this says is that if I do C1 plus C2, if I apply F, which in this case is addition, if I apply this to C1, C2 and get C3, if I decrypt C3, what I should get is M1 plus M2. Okay? If I have this, I call this is a homomorphic on the operation of add. And if I have this for example, multiplication as well, then I basically can do any linear operation on this system. But what I'm saying is that this homomorphism not necessarily applicable to any systems. For example, for RSA, there's homomorphism on multiplication, but there's not homomorphism on addition. Why homomorphism matters? There are lots of things that actually can use homomorphism. But what you need to focus on for now is the correctness, that any crypto system has to have this correctness property. If it doesn't, then the system is not usable. Okay? So now that we know that we need a system that takes the key and the message and create the ciphertext, now the million-dollar question becomes, what is a secure algorithm? What is a secure encryption algorithm? If I have an algorithm, how do I know it's secure or not? Any suggestions? What do you call a secure algorithm? Yeah.
You cannot decode a encrypted message without being given the key in a normal amount of time.
Yes. So you cannot find the message without the key in normal amount of time, in bounded amount of time. Any other suggestions? That's fairly accurate. Let's actually, if you want to understand why this is the case, let's first talk about the attacks, okay? So there are a whole bunch of different attacks that we can do, and I definitely recommend you to kind of like do crypto analysis, like Google crypto analysis, and you will see different things. Like there are things such as frequency analysis, brute forcing, depth analysis, differential analysis, and so on and so forth. For example, the ones that's very, very popular is the frequency analysis, right? So for example, you know that in English, the character, the letter E is the most common one. And then after that is T, and then after that is A, okay? So what you want to do, for example, for the Enigma machine is trying to say that, okay, probably the most used character is going to be E, right? So even if I kind of map various different words to various different ones, the distribution won't change, right? Because still words are in English, and then I'm going to encrypt them into some like gibberish or something. But still the distribution of those would be something very similar to this, right? So what I can do is that for this Enigma machine, for example, I can first figure out among this encrypted sentence, although I cannot really read it in English, I can try to count the number of repetition of every single character and say that the one that is kind of repeated the most is most likely E. And then like, work my way from there, basically kind of doing the reverse engineering of the characters, okay? This is what we usually call a frequency analysis. And this frequency analysis is kind of combined with what we call a brute force. So essentially, we just try all the options and see which one works. So for example, I don't know really this mapping, but what I do is that I check different combinations and see whether the new sentence makes sense or not, right? Only one particular mapping would make sense, usually, right? So as a result, that's how I know that I find the answer. So to kind of answer the question that I asked, based on this kind of like possible attacks, really what Andrew is saying is correct, that it should be hard to completely determine M without the knowledge of K when we are given C, okay? But if we want to be more accurate, there are a whole bunch of things that we need to think about. So first of all, what do we mean by determining M? Do we mean full or do we mean partial? So for example, if I have this, like, let's say 8-bit ciphertext, if I know, let's say it's a sentence. If I know one character, like I know that the first character is an A, I have no idea about the rest. Do you think this is a secure crypto system or not? How many of you think this is a secure crypto system? Okay. So there is this notion of partial versus full. It depends. There might be some particular cases this is a secure system, but in most cases we don't really assume that this is a secure system. Why? Because let's, for example, say that I know whether this is Y or N. Okay. And then somehow I managed to know that every single sentence start with yes or no. Okay. And then let's say, for example, I have another information that I know that no means not attacking and yes means attacking. This is actually a real example that in some of these battles in Pacific Ocean, they were breaking this information that they didn't know really what the message was, but they know for a fact that this message means to go. So they knew that they're going to attack some of the ships in the Pacific Ocean for the U.S. For U.S. Navy, and they knew that sometimes this is going to happen. Okay. Then what they figure out was that once that message received, they know that this is the time. Okay, so they were prepared. So there's kind of like some of these partial informations are actually quite helpful. For the Enigma machine, actually, if you search, you will see that the reason that they find the actual, the way that they broke it eventually, partially was because of the Turing machine that Alan Turing was kind of like built. The other reason was apparently like the first word, like the first sentence of all their messages was like Heil Hitler or something like that. And they knew that, and their search space becomes so much smaller. So they figure out that, okay, I need to first figure out what is age, for example, like what is mapped to age. And they did that, and then boom, they managed to kind of break the system. So systems that are kind of even partially you can, I'm just deleting this and will not become a, anyway. So partially versus fully is very important because sometimes even one single bit could reveal very, very important information, okay? The second thing that's very important, and I'm going to talk about in this lecture and next lecture, is what is the attacker's capability? And there are three things that are really differentiate different types of crypto systems from each other. There is what we call ciphertext only, known plain, ciphertext CPA attacks or chosen plaintext attacks, chosen ciphertext attacks, and known plaintext attacks. Okay, so the difference between them is that it's just as the name suggests. If it's a chosen plaintext attack, it means that the attacker has this capability that they can choose whatever plaintext that they want, and they can see the corresponding ciphertext of that. In other words, the attacker can encrypt somehow any message that they want. Okay, a more capable attacker can do what we call a chosen ciphertext attack, which means that not only they can pick whatever plaintext that they want and they can encrypt the system, they can also decrypt the system as they wish, which means that they can choose the ciphertext and say, okay, give me the plaintext for this, okay? And you might ask, okay, if I can do encryption and decryption, doesn't mean that I actually do anything. No, the big difference is that it's only for limited pairs, which means that somehow I have this magical kind of oracle that I can ask and it can give me the outputs, but only for limited, let's say for 10 tries or 20 tries or 100 tries, okay? And then the non-plaintext is like the weakest among all, which means that I only know what is the plaintext for this particular set of ciphertext. I cannot choose arbitrary plaintext, but I know, for example, this ciphertext is coming from this plaintext, okay? So that's the difference between them. This is frozen. Okay. So what we call CPA secure, CCA secure, and just known plaintext. Okay. For now, for symmetric key encryption, we usually focus on CPA secure, chosen plaintext secure systems, which means that I can choose whatever plaintext that I want. I can encrypt it, but I cannot do the other way around. Okay. So when we're saying the system is secure, we should go for this. Okay, we should be able to be chosen plaintext secure. Okay, and then one thing you want to, as I said, you can think about this is if I cannot really understand anything from the ciphertext, is that enough? Is that considered secure enough? And in order to understand the difference, let's say that I have only 2 messages, okay? And I encrypt each message and get C1 and C2, okay? So if, let's say now I see a ciphertext, and then since I only have 2 messages, the ciphertext could be either C1 or C2, but let's say the attacker does not know which one is which, okay? So if by seeing C, the attacker can do better than random guess, which means that, for example, the attacker knows that there is 51% chance that this is coming from M1, and there is 49% chance that this is coming from M2. Then we also call this not secure cryptography system. Why? Because think about this again. Think about the yes/no example. If I see the ciphertext and know more than 50%, better than a random guess, that this is probably yes, then my crypto system is not secure enough, right? So there should be exactly 50% accuracy or very close to 50% if I want to be very accurate, that I cannot tell whether this is C1 or C2, just only for 2 messages. In more formal form, we call this perfect secrecy, and the definition is that for all M0 and M1 from a set M. So let's say all the messages that we can encrypt, okay? Let's say all the words in English. And for all the ciphertext in the ciphertext domain, and a random variable k, which is the key, that is uniformly distributed over k, so which basically we can choose any key, then we have what we call perfect secrecy if the probability of the seeing C becoming from M0 is exactly equal to the probability of C coming from M1. And as I said, this is for all M. So any pair should be exactly equal amount of chance, okay? If I have this, then I will have a perfectly secure crypto system. That's what we want, okay? That's the goal of any crypto system, that no matter which 2 messages I use, if I encrypt them, if I see the ciphertext, I should not be able to tell which one is coming from which one. Okay, that's what we are really looking for. Okay. So then the question becomes, is that can we achieve perfect secrecy or not? What do you think? Do you think we can achieve perfect secrecy? How many of you think yes? So most of you think no? Well, the answer is actually yes. We can achieve perfect secrecy. And surprisingly, perfect secrecy can be achieved very simply. There's this thing called OTP, or one-time pad, which basically says that if I have a key, okay, if I just XOR this with my message and get C, as long as the size of the message and the size of the key are the same. So for example, if I have 32-bit message, I have exactly 32-bit key, then this ciphertext is going to have this property. If I build a crypto system, I'm going to get this property for my message. As long as my messages are uniformly distributed and so on, that's there. As I said, I'm not really doing very formal description, but as long as these are uniformly distributed in their own respective sets, then I'm going to have perfect secrecy using one-time path. Okay, so that's great. That seems that we don't need to do really anything. And then basically our encryption system would be this, right? So our E of M and K is just C is equal to M XOR K. And is there anybody who's not familiar with what is an XOR? Is it good? Okay. And what would be the decryption for this? It would be again XOR actually. So the decryption would be XOR of C and K. The reason is if you XOR something twice, you get your number back, right? So like XOR of 1 and 1, like, if you XOR 0 or 1 with any number twice, you get your number back because these two kind of cancel each other out, and then you're going to get your number back. Simple logic. So one-time pad, or OTP, as we're going to call it, is actually very, very simple, and it's very, very powerful because it gives us perfect secrecy. The catch is that thing that I casually said, and that was that the key and the message should be same size. Okay. So why this is a catch? Because think about encrypting your hard drive. 1 terabyte of data. How much data do I need for the key? I need another 1 terabyte just for the key. And that doesn't work, right? Think about every message that you want to send, you have to somehow send a big key with it, right? And you cannot repeat the key because, as I said, the key has to be randomly chosen, has to be uniformly distributed from the domain. So the problem with the one-time pad is that the size of the key should be the same size as the message. And if the message is short, great, use one-time pad. But in reality, your message is going to be long, it's going to be repetitive, so one-time pad wouldn't work, okay? And then the second problem with one-time pad is two-time pad or many-time pad. So if I do yes with the key K, okay, I'm going to get a number, okay? And then I'm going to get C1, for example. If I do this tomorrow with the same key, I'm going to get the exact same C1, right? And remember, I told you before that even though I don't understand C1 and C2, but if I can somehow find the distribution of C1 and C2, I can find something about the system. So for example, if I know that 4 times I'm going to say yes and 1 time I'm going to say no, by just seeing C1 4 times, I know for sure that C1 is yes, right? So the problem of one-time pad is that it's not repeatable. In other words, one-time pad is what we call a deterministic crypto system. What we want to do is a probabilistic crypto system, which means that if I encrypt yes today, if I re-encrypt it 1 minute from now, I should get a different answer. It might sound counterintuitive because you might wonder, okay, then how do we know that these are the same things? But we're going to actually show you how we're going to achieve this probabilistic feature of a crypto system, because I cannot encrypt the same message twice and get the same ciphertext. If I do, then my crypto system is not secure. So how do we do this? I'm going to talk about this in next time. Okay.